Hi everyone, I hope you're all doing okay. It's been a while. So, as a reminder, I'm Edmond, also known as ESR number 10, I guess, amongst the many nicknames I apparently have. I'm doing my PhD at the University of Twente in the Netherlands with Edmond as my supervisor. And now I'll be presenting this progress overview titled Non-Reflective Boundary Conditions in the context of the Discontinuous Calorican Framework. As an overview, in this presentation, I'll start off by explaining the objective of our work before proceeding with the methodology phase, in which I'll present the governing equations of fluid flow that we're working with, then the spatial discretization method that we use, and non-reflective boundary treatment. Then we'll see a few animations about the results in both 2 dimensions and 3 dimensions, utilizing 2 different discontinuous Galerkin solvers. And finally, I'll wrap it up with a conclusion serving as a summary. So while most of everyone else in Magister is, in one way or another, involved in thermoacoustic instabilities and/or machine learning, my work isn't, per se, at least not directly. What we're mainly interested in is further extending open source tools to better simulate fluid phenomena in turbomachinery applications, which in the context of Magister is the combustor part. More specifically, we're heavily invested in high-order methods. So why high-order methods? Because as opposed to typical lower order ones, they're usually more computationally efficient and have desirable properties such as less numerical diffusion and dispersion errors. Why non-reflective boundaries then? Well, let's put it this way. What use is a high-fidelity solution if the results themselves are contaminated by spurious reflections due to open boundaries? In this work, we use the discontinuous Galerkin method as a high-order method and a perfectly matched layer and characteristic boundary conditions as non-reflective boundary treatment. The equations we're dealing with here are the Navier-Stokes equations in their compressible form. Here, they're represented as a function of the working variables W, which could either be the conservative ones, U, or the entropy ones, V. And all the variables have their usual meaning. Now let's talk a bit about the discontinuous Galerkin method first. So, what is it? It's a spatial discretization method that, briefly speaking, is similar to the finite element framework, yet borrows certain enticing properties from the finite volume literature. Some of its advantages are, much like both its counterparts, it can handle complex and unstructured grids. It is highly parallelizable due to its compact nature, and it is very stable for convective-dominated PDEs, such as the Euler equations. Some of its shortcomings, however, are the obvious extra memory storage requirements, and it is relatively expensive for elliptic-type PDEs. For example, when evaluating the internal viscous fluxes on an element. To proceed, there are usually 2 variants of the discontinuous Galerkin method, its nodal and modal forms. Talk about confusion. In terms of the working variables W, they are represented both here. The modal form, with an M, is based on a polynomial expansion that uses psi, which denotes the Legendre polynomials. The nodal form, with an N, uses L, the Lagrange polynomials, to directly use the nodal solution itself in the expansion process. Either way, both variants are linked via the Vandermonde matrix. As for the nonlinear flux evaluations, the inviscid or Euler ones rely on a Riemann solver, while the viscous fluxes utilize the symmetric interior penalty method. That way, each element's solution, though discontinuous at its local boundary, is guaranteed uniqueness, and in turn a well-posed formulation is achieved. Next, we move on to non-reflective boundary conditions, also known as far-field or open boundaries. So what exactly are they? The idea behind them is pretty straightforward, though, to mimic an infinite domain, in a theoretical sense, that is. This basically implies that all the information should travel only out of the domain, without admitting any reflections back in whatsoever, hence the name, non-reflective. Many approaches do exist. Some use extrapolation methods, while others make use of characteristics of the PDE itself. Other methods are more intrusive and may be categorized under so-called buffer zone techniques. In these sort of methods, the idea is simple: to extend the domain into a fictitious region in which the governing equations are modified in such a way to reduce or eliminate any reflections back into the physical domain. Some progressively increase the flow speed into a supersonic regime, while others apply damping terms in that region, be it bluntly or carefully, as is the case with the PML. Speaking of which, what is this perfectly matched layer, or PML for short? So far, we know it's a buffer zone technique that damps the solution. However, unlike other straightforward damping methods, the PML damps the solution exponentially while matching the solution at the interface, or non-reflective boundary condition prescribed. This matching property is, by construction, what guarantees no reflection back. As an example here, consider the figure on the left. Say we have a box in which we need to prescribe a non-reflective boundary condition on its rightmost face. Using the PML strategy, we essentially extrude the domain adjacent to this boundary condition into a fictitious region, where, in it, the solution is exponentially damped while respecting the matching property at the interface. Let's delve a bit into the details of how a PML really works. So to set up a PML, first off, we extrude the fictitious domain next to the non-reflective boundary condition prescribed. Then we apply a spacetime transformation to our PDE in order to ensure that the phase and group velocities in the dispersion relations are aligned. Otherwise, for certain wave number and frequency combinations, the formulation becomes unstable. Afterwards, we follow the usual three-step method. That is, convert the original PDE to frequency domain, apply a complex change of variables into the differential operators, then revert back to time domain in the original variables. The resulting set of equations are that of the PML that damp the solution with respect to a target state. The target state is usually taken as the mean state. A few things to note, however. Besides the extra computational resources needed for nonlinear PDEs, the perfectly matching property is no longer maintained. With that being said, empirically speaking, given the results produced, the benefits greatly outweigh the costs. The next set of non-reflective boundary conditions implemented is that of the characteristic boundary conditions, or Navier-Stokes characteristic boundary conditions, in the context of the Navier-Stokes equations. So how does it work? Well, we directly impose the boundary on the face itself. No extrusion is needed. The method is based on characteristic analysis, hence the name, whereby the incoming or unknown data are estimated from the interior known data. In its basic implementation, as Professor Poinson introduced it, this is based off of the so-called Lodi assumptions at that boundary, which are short for local one-dimensional and implicit flow. More recently, there are many variants that improve on this by adding the contributions from the transverse terms. In the context of the discontinuous Galerkin method, we apply this via a polynomial correction approach. We first assess our solver on classical benchmark cases in 2D, such as the inviscid isentropic vortex being convected out of a domain. The vortex is superimposed on a uniform flow with a Mach number of 0.5, moving from left to right. All four sides of the square are non-reflective boundary conditions, with the left being an inlet and the remaining three outlets. In the physical domain, the same configuration is used for both simulations, that is, 12 by 12 elements, each described by sixth-order polynomials. Additionally, in the PML region, two layers of elements are used, each of third order. The right figure is that of a PML, while the left uses a characteristic boundary. In both cases, only the physical domain is presented. What you're seeing is a density with the u-velocity contours on top of it. As the movies do show, both boundary conditions manage to preserve the vortex as it is being convected out. Another interesting and challenging benchmark problem for open boundaries is that of a shear flow with vortex rollup. In this case, a velocity profile with an S-shape ranging in between 0.2 to 0.8 is specified. A Gaussian source term is added to the energy equation to excite the Kelvin-Helmholtz instability, which in turn will induce vortex shedding. The physical domain in both simulations is comprised of 28 by 16 elements, each described by a fourth-order polynomial. As for the PML, 2 layers of third-order elements are used. Similar to the previous example, an inlet is prescribed on the left, while the remaining 3 sides are outlets. What you're seeing is a density and pressure contours added on top of it. Throughout this period of simulation, both boundary conditions managed to mitigate most reflections. However, the characteristic treatment, as opposed to the PML, did not convect the vortices at the proper speed. This is evident from the pressure contour peaks and later confirmed when compared with the reference solution, taken from an extended domain using the same spatial resolution. We now move towards yet another benchmark problem, this time in 3 dimensions, with a flow governed by the Navier-Stokes equations. In this setup, a spherical pressure pulse is superimposed on a quiescent flow in a cube. Quiescent, meaning the flow is stagnant. The idea is the acoustic pulse should radially evolve in time and eventually move out of the system. Such a problem is typically used to assess the efficacy of edge and corner treatments in non-reflective boundary conditions. The domain is composed of 12 by 12 by 12 hexahedral elements, each described by a fifth-order polynomial. All 6 faces of the cube are prescribed as non-reflective outlets. The figure on the right is that of a Navier-Stokes characteristic boundary treatment, which uses an optimized transverse term inclusion, while the figure on the left uses an extrapolation method based on the Riemann invariance. And unlike the NSCBC, the extrapolation method does a terrible job in attenuating the reflections. Finally, in this example, we consider more challenging and complicated problems involving turbulence. The example chosen is that of the NASA hump case, whereby a flow is subject to a bump that will perturb the flow and induce turbulence. Such a problem is usually used to evaluate turbulence models. The flow is initialized with a Mach number of 0.1, moving from left to right. The top boundary is an inviscid wall, while the bottom one is a viscous wall. The spanwise directions are coupled via periodic conditions. Towards the left, an inlet is prescribed based on total conditions, while an outlet is used on the right. Unfortunately, due to computational constraints, the grid is still 2 cores. This is observed when comparing with reference experimental data. That being said, the main motive was to compare the effectiveness of the characteristic treatment as opposed to the extrapolation one. All figures depict the instantaneous pressure taken at different times. The bottom figures also include the Mach number at the bottom wall, near the hump. Despite using a relatively coarse grid and placing the non-reflective boundary conditions relatively far, the contamination due to the numerical reflections are still very evident in the pressure waves. This is especially noticeable for the extrapolation method. As a conclusion, in this work, both PML and NSCBC boundary conditions prove very effective. The latter is especially true when compared with the standard extrapolation technique. In all PML simulations, characteristic boundaries were used as terminating boundaries to further reduce the fictitious region. Future work will include the addition of compatibility conditions to the NSCBCs, as well as the implementation of the PML in 3D generalized coordinates. Then, test this whole machinery on more challenging test cases, such as the T106A turbine cascade and the combustor. And that's it for now. Thanks for listening.